I guess it's going to be interesting. So I'm going to talk about some joint work with Andrew Ross, Pavel Perez-Hogan, Zewili, and Carlos Fernandez-Granda here at NYU on our use of data and machine learning together with theory to come up with mesoscale eddy parameterization. So, a little announcements. Jenny gave a wonderful talk yesterday about some of her work as part of the climate process team. So our annual meeting is coming up in May in Woodsong. So please feel free to register and submit an abstract. It's going to be a hybrid, but it'd be great if many of you were able to come in person. So we'll talk a lot about, all the themes that you are already discussing in Hamburg and then some. So today, rather than talking about, our work in the climate process team, I'm going to talk about a different, branch of our work on eddy parameterization. And it's part of a large effort supported by Schmidt Futures on improving climate models and subgrid parameterization for the ocean, sea ice, and atmosphere. So we're about 50 people now. It's pretty exciting, many institutions in the US and France, and really trying to tackle this problem of, parameterizations in multiple component of Earth system models with machine learning and physics. So I'm going to focus on this project, or one part of this project in particular, ocean eddies, which are close to my heart, I would say. I've been working on that for quite a while, so I'm just going to give a little intro about, eddy parameterization and backscatter. I mean, again, Jenny gave a wonderful long introduction yesterday, so really I would not do it justice if I try to do the same. What I'm going to focus on is really kind of almost our philosophy about how can we use data and machine learning to come up with new parameterization of mesoscale eddies and backscatter, and what they do well, what they do poorly, and where I feel there is a lot of avenue and room for improvements. And I'm going to talk a little bit about some initial, tests that we've done with those data-driven closures in MOM6, which is the ocean component of the GFDL and now NCAR model in idealized settings, and tell you a little bit about where we're going from there. Okay. So, a simple plot, so to speak. I think this plot became quite famous by now. So by Bob Alberg, showing the grid resolution required by a simulation to resolve the bioclinic deformation rates, right? So, I mean, again, I probably don't need to argue with this audience. In many places of the world, 1 degree or quarter of a degree, which is kind of the nominal resolution of today's climate models, is actually too low to resolve eddies, or the way we would want them to be resolved. And so, here you can see in the Gulf Stream region, for example, would need resolution that is far higher than the resolution of a typical upper climate model today. Increasing resolution, of course, means increasing computational costs, but what we have to do is something in the middle, where we try to represent eddies, in a way that will mimic the impact on the large-scale flow, especially in regions where eddy activity is high. So Gulf Stream, high latitude, Southern Ocean, and many other places where we know that the eddy mean for interaction is actually quite important. So typically the way all of us have done eddy parameterization is by using theory, right? Try to come up with a simple mathematical model that will represent those missing scales. So here we're trying a different paradigm, where we say, well, we have a lot of numerical simulations, right? And, in some instance, we have actually observations, but we have a lot of numerical simulation that we can't run, for hundreds of years and do large ensembles, but we can still run them, over a short amount of time or as a one-shot experiment. So can we use that data to actually try to capture the effect of resolved eddies in those simulations on the large scale flow? And then can we use machine learning and kind of new algorithm to capture the effect of those eddies on the large scale flow, and then come up with a parameterization. So rather than, a priori deciding what is the mathematical operator that I should be using, let's just let an algorithm figure it out in terms of giving him some input, which is going to be the resolved scale, and the output is going to be the subgrid closure, in our case, mesoscale eddies. This idea is not new. Using machine learning and data to do it started in the late 90s, especially in the atmosphere, looking at radiation, for example. And of course, in the last few years, clouds, warm rain processes, and in the ocean, quite a few of us have been working on eddy closures for the last few years. So really lots of people kind of trying to leverage, data and machine learning algorithm to try to come up with subgrid parameterization or subgrid closure without any a priori. So now, right, so up on top is really kind of, the machinery behind it, right? You have some resolved scales, try to come up with something either in your head or with an algorithm that will represent, a closure. So, Jenny yesterday and, many people in the audience, Stefan and others are using anti-viscosity, right? So it's kind of a simple backscatter that in my, little schematic here of error versus complexity will sit up here. So what do I mean by that? So error versus complexity. So complexity, I think about it in terms of the number of parameters. If I have a physics-based parameterization where I try to actually mimic backscatter, so the inverse energy cascade, right? So reinjection of energy at a scale that is slightly larger than dissipation. Then again, to first order, I have one parameter. It's tunable, but it's still only one. The problem is if you try to feed that across all, regions of the world, then, your error is probably going to be pretty large because, there is non-local effect, as again, Jenny mentioned, some are local, some, depend on different properties of the flow. On the other side of the spectrum, you could use, modern machine learning algorithm where you have a bazillion number of parameters. So it's going to be a lot easier to actually fit a function that will represent your closure at every single point on the globe. Now, the problem with that is you have absolutely no clue what the algorithm is figuring out and, why is it useful and, how trustworthy it is. So we've been kind of settling in this part of the curve of error versus complexity, where we're trying to get a model that is as sparse as possible with as low error as possible in mimicking the effect of the eddies, and that is interpretable. So what do I mean by that is we actually, rather than imposing a functional form for the algorithm, like we do when we have physics-based parameterization, we let the algorithm figure out an expression, so an equation, and then fit some parameter associated with that. So there's something in between here where we try to bring our, kind of physical intuition after the fact to make sure that we actually understand the model that we're getting. So what I'm going to do is to demonstrate a little bit those kind of three methods. So how a backscatter, an equation discovery, and a deep learning parameterization do in a simple QG model, which is kind of the bread and butter of, eddy mesoscale, theory. So first algorithm in this kind of, sorry, let me go back here. So first algorithm to discover equation, it's something we've done a few years ago with my former PhD student, Tom Bolton, is to use something that is called sparse regression. So what do? We have some high resolution simulation. We're going to diagnose, a subgrid closure. So we're going to diagnose the, basically the resolved advection from the high resolution grid that would be missing in a coarse resolution model. So we diagnose that eddy forcing. So basically whatever we're trying to, capture in a coarse resolution model, we're going to feed that to the algorithm. And we're going to ask the algorithm to come up with a parameterization given a set of basis functions. So what are the basis functions? Something we predefine. We say, well, we know that it's probably going to depend on, gradient of velocities, temperature, higher order, strain, shear, and so on and so forth. And the algorithm is actually going to try to minimize the error between our diagnosed subgrid forcing, our diagnosed subgrid eddy forcing, and this kind of set of basis functions. So it's going to go through a library of function and just pick out the functions that best mimic the data and are missing closure. And so again, everything is done as a function of the resolved scale based on high resolution output. And so you prune that kind of library of function and you make a little bit of a decision, right? How many terms you want to keep, do they make sense, and so on and so forth. So by doing this kind of procedure, we end up with a very nice expression that, of course, we rewrote and did a few a few mathematical manipulation for it, and we end up with basically the divergence of a symmetric stress tensor that depend on shearing and stretching of the flow field and the vorticity. So we were able to actually interpret each one of those terms in the equation And that tells us actually when energy is being re-injected into the flow, at which wave numbers, and how the energy is actually being distributed. Now, the downside of this approach is I had to preload the library of function. And the disadvantage of that is, first, I'm already putting some bias because I'm telling the algorithm what should be useful. So, if you trust your parameterization, then you trust the physicist, and it's great. But maybe we're missing something super important. The second thing is just a practical one, is that we need to preload that library of function. That means we need to calculate it, and we need to give it to the algorithm. So that means the computer. So the amount of data you need to save actually is pretty dramatic, the more library of functions you want to actually feed your algorithm. So we went down another path, which is called genetic programming. So in this case, it's purely symbolic, operations that are, kind of generated by the algorithm. So what do? We still start with some input, variables. We still diagnose the subgrid forcing. And then the algorithm is going to randomly seed, a few trees, and it's going to go down the trees and do addition, multiplication, division, and so on and so forth. And you're going to have many of those trees here. And again, it's going to be basically randomly selecting some of them, creating some mutation, cutting some trees, adding some branches, until it basically finds the optimal combination that is the sparsest possible function. So now this sounds like almost magical, right? And almost is, right? You find kind of the best program that will describe your data set based on a bunch of symbolic operations. Now, the downside is it wasn't made for physics problem. So that means that we had to actually modify it for our test cases. So the main changes we introduced is, one, taking spatial derivatives. So here we did it in spectral space because the model that I'm going to show is in spectral space. And of course, that means that accuracy of the derivative is much higher than if we were in real space. Second thing we introduced is actually doing it as an iterative process. And so why did we do that? Is because when you keep going down those kind of random trees and branches, the first few terms that the algorithm finds are always the same every time that you regenerate a new seed. But then when you go deeper, it becomes less and less robust. So we were a little bit worried that we were actually just capturing a bunch of noise. So what we've done is, we went down the trees, selected the first few expressions, then, put that aside, calculating a residual, and then learning the residual. And so this kind of a sparse, iterative process. And the third thing that we've done is what we call the human in the loop intervention, meaning we actually made the algorithm stop when it did something stupid, like adding vorticity and, and velocity together, which don't have the same units. So if you didn't do Buckingham pi, ahead of time by normalizing everything, then you end up with an issue. So down here is, one of the expressions that we discover. If you worked on mesoscale eddy parameterization for a while, you probably recognize quite a few of those terms. Some is the, negative viscosity. Some is actually kind of Smagorinsky. One is, anticipated potential vorticity, kind of, from Vallis and others. And there are a couple of other new terms that, we were able to interpret in terms of their momentum energy transfer. So let's look at what they do now. If I take a simple QG model from which, I've learned the parameterization, how well is the closure doing here? Here's a high resolution simulation. So it's basically a snapshot of potential vorticity in our, truth case. This is a low resolution simulation. So same PDE, right? So basically 2-layer QG, doubly periodic, flat bottom, just lower resolution. So again, just snapshots. Now we're going to take the low resolution and we're going to implement backscatter. So Jensen and Hell, negative Laplacian, of Q. Here's a neural network. So one for which we actually train a full-blown deep learning algorithm with a bazillion number of parameters. And here is the coarse resolution model with our, equation discover parameterization. So, I mean, if I look at by eye, they all kind of look good, right? They all improve the flow. There's more turbulence. We look at something a tad bit more quantitative. So we have done here kinetic energy as a function of time. The black line is the high resolution simulation. Coarse resolution is in gray. So as we all expect, less kinetic energy in the coarse resolution model. Each one of the parameterizations, so deep learning is in green. Orange is the sparse equation discovered, and blue is Jensen and Held. Each one of them improve the amount of kinetic energy in the flow, but they all do it at a different rate, right? So the deep learning algorithm actually shoots off super quickly, at the spin-up phases. The other ones are a little bit slower, but they still overshoot, initially, and then kind of stabilize slightly below the true model. We didn't do any tuning here, by the way. We learned from data, we stick it in, and that was it. Only for Jensen and Held, we did a little bit of tuning to try to get the best possible answer. If I look at the probability distribution of the potential vorticity in the upper layer, so again, PV, upper layer, gray is coarse resolution, so you have more things around 0, and the tails are cut. At high resolution, then you have longer tail, right? Which again makes sense, you have more turbulence. So the best parameterization, if you look at this metric, is going to be the neural net, actually. That's the one that actually reproduced the best PDF, even though it was a little bit, messy in the initial cases. While the two others that iEquation discovered are doing a little bit, more poorly, I would say, in part of the spectrum. So depending on the metric that you look at, some do better than others, and it's all by eye here. We've done things that are more quantitative. Let's look at something that is actually what the parameterization are supposed to do, right? They're supposed to actually improve the energy budget. They're supposed to really mimic backscatter, meaning extracting energy from AP into kinetic energy and putting it back upscale. So here are the different terms in the spectral budget. So we have spectral fluxes as a function of wave number. Let me just concentrate on this panel over here, which is the kinetic energy flux. So where it's negative, we're removing energy. Positive, we're sticking it back in. So we're taking energy from the small scale, putting it at large scale. Coarse resolution is in gray. Black is the high res again. So obviously at coarse resolution with no parameterization, right, you have a lot less kinetic energy flux. Each one of the parameterization kind of improve that. So they all do very well at improving backscatter, and they do all very well across the full energy spectrum. Now, obviously, again, it's kind of obvious if you do one of them well, you'll probably do the rest of them well because it's a very simple two-layer QG model. But still, right, the closures are doing the right thing. The difference is, Jensen and Held has one parameter. The deep learning network has, I can't remember how many, but tons. And the equation discover as just a few more, but a few more than the Jensen and Held, but only a few. And so they all do kind of equally-ish well. Now, what happened if I take those equation discovered one or the physics based one and implement them? It's still a QG model, but now rather than being rather isotropic type turbulence, we have jets. So let's have a look. So again, I'm not going to retrain, I'm not going to retune, I'm not going to do anything else. I'm just going to assume that, at the end of the day, the level of energy I'm trying to represent is the same, and the inverse cascade is the same. So a jet configuration at high res, low res, and now we're going to take Jensen and Held, and then our two data-driven parameterization and implement them in that, jet configuration. So here's what we get. Jensen and Held, I would say almost do nothing. Very little, so we would need to crank it up quite drastically to actually start getting something useful. The deep learning one is just a disaster, right? It actually tries to push the model into a kind of almost isotropic state rather than keeping the jet in place. While the equation discovered one, actually, again, without retuning, with just 5 parameters, does really well. Actually, can pretty much capture the jet, the jet configuration that you have at high resolution, again, without additional computational cost, because, a parameterization that has just a few terms is actually a pretty good one. So, all of that was done in the QG model. So, for us, it was more as a way to try to test, and push the boundaries of what you can do with data, what they do well, what they do poorly. But, another part of, our philosophy is at the end of the day, it also has to work into a real code, right? So we started with idealized simulation. We are now, I've actually runs in a global configuration, but I can talk about it another time. So let me show you 2 machine learned parameterization in MOM6 in a double gyre configuration. So again, kind of very simple. So longitude, latitude over here, wind forcing, 2-layer, it's basically stack shadow water. This is a 1/32 of a degree. This is a 1/4 of a degree, and we're looking at sea surface height as our variable. And so what we've done is we've done two tests. One where we take the coarse resolution model, where you can see we have a standing meander here. We have standing eddy that, and the jet is, relatively weakish compared to the high res. So we took this coarse res and we implemented two parameterization. One that was learned from GFDL CM 2.6. So they, basically 1/10 of a degree high res, coupled climate model with a neural network. So tons of parameters. And we implemented as an ensemble run because it was derived as a stochastic parameterization. So here's the first implementation. So again, just looking by eye, you can see that the standing eddy is gone. The jet meander looks a little bit more like the high resolution. And just again, this was trained on a completely different data set, which is completely unrelated to the model that we're actually implementing it. Which again for us was kind of a high bar to pass, and we were kind of pleasantly surprised. Obviously, we had to tune it here because there were some weirdness happening. So just want to make that clear. But nonetheless, I'm still surprised that it's actually working, but pleasantly surprised, I would say. The second one is one of the equation discovered one. So again, we take the coarse resolution model, and now we implement an equation discovered parameterization. Again, it was trained on completely different data, and now it's
5 minutes.
Yeah, that's perfect. I'm wrapping up. And now it's implemented into the code. Okay, now I forgot what I want to say. So yeah, so here what's quite simple about it is it's an equation. So when you try to implement a neural net, you have basically an additional barrier, especially the kind of neural net that we actually trained. It's a convolutional neural network. So it's has a lot of non-locality, and you need to go back into your Python code to actually do the inference at every single grid box or places in the ocean. For the equation discovered one, well, as we all used to, it's pretty easy to code up, right? So there is no overhead, so to speak, in actually implementing that. So that's a big plus. That means that any of you can pick it up and try to implement it if you're interested. While for the neural net, you can do that. It just requires a little bit more effort, to actually interface between Python and Go. Not impossible, but takes more work. Now, I always kind of joke around, is machine learning, basically our savior, and then we're all done. Actually, we actually faced some of the same problem that many of us have faced, which is, numerics and stability are always an issue, right? So we had to tune down some of the things. We had to do some filtering, which I know that Stefan talks a fair bit about this in some of his papers, when you implement backscatter, depending on the numerics that you have and the grids that you have. So we had to do something similar. If you implement that in a real model, compensating error will also come into play. And of course, calibration, tuning, generalization, all that kind of stuff is also a question, right? So, I think we're still working on this, and it's all of that work is actually done, in terms of implementation by the Princeton GFDL team with Cheng Zhang and Alistair Adcroft, and then Pavel Perez-Hogan at NYU has been doing the equation discover implementation. So it requires, still a fair bit of effort, even after you trained, parameterization. So let me wrap up. And hopefully I gave you a bit of a flavor. So, I think with this audience, I don't really need to argue why parameterization of eddies are still in demand. Again, you've heard many talks, and I'm sure you're going to hear more today and tomorrow. And, our question was a little bit, can we use data and machine learning to actually improve upon what we've done so far? So it's not magic, right? It's not going to solve all of our problems. I always say, I still develop physics-based parameterization myself and run model hierarchies and all that kind of stuff. But it's still a new tool that actually helped us, poke around new ideas and really try to surpass, where we've done well, but where we could do better. So I see it as a little bit of a way to kind of, push us around a little bit and try to put us outside our comfort zone and think about it a little bit differently. So, I talked about deep learning, it's really cool and it's everywhere. Has very high skill in general because you have a lot of parameters, but it's hard to actually interpret, and generalization is not always obvious because you train it so much on a given state. The equation discovery one, as a kind of a trained climate physicist, I guess I enjoyed that part very much because you come up with equation and then you need to scratch your head for quite some time to see if it makes sense. It's a little bit different than the way we used to, but I still find it, quite enjoyable. And the question is, of course, Are we learning new physics in terms of scale interaction, different processes interacting with one another? And, in some cases we have, in some cases we didn't. But, nonetheless, I think it's part of the, scientist journey to try to actually think about stuff differently. So still lots of challenges and opportunity. So for people who like physics and, data and algorithm, I think there's a lot, to be done. But I also won't lie, and there is also a lot of noise, with everybody using machine learning. There's always kind of these risks, but, how can we find the best, way to get people excited, in both doing theory and, data-driven algorithms. So I think lots of stuff to do and very exciting time. And again, I'm going to plug in, a few resources if you're interested. We do everything kind of, open source. We have some kind of Jupyter book where we try to teach people machine learning using Lawrence 96 and parameterization. We have algorithms and a bunch of stuff. And as I mentioned up top, our annual meeting of the CPT is coming up. So please join us. And I'll leave it at that and happy to take questions.